these great IPA beers out there, so that's unfortunate. But, well, so for those who don't know us, so Classic is a quantum software company. We are based in Israel and in the US, employ over 30 quantum software engineers, and our quantum algorithm design platform is being used in several industries and academia. So we all want to be quantum ready, right? And sorry, I'm going to oversimplify quantum readiness. Basically, it's about hardware and software. I'm not going to speak about hardware, not because it's not important, it's very important, because we trust the hardware vendors, right? We see the progress, more qubits, better quality, and we have good reasons to be optimistic that in the next couple of years we'll be able to run complex circuits for hundreds and even thousands of qubits. And then it would be a fair question to ask, are we ready for these circuits? And the answer is probably not, because with existing tools and methods, it's reasonable to build small circuits, toy circuits on 5, 7 qubits. It's very challenging to build complex circuits for a few dozen qubits, and it's almost impossible to scale, right, to hundreds and thousands of qubits. And I want to give one example to show that. So this is a simple oracle. You know, that's a nice exercise for everyone who starts with quantum software. So basically what you want to do is to design a small oracle that marks 2 states out of 8, right? Because it's 3 qubits. So this is nice. This could be hand-coded, but now let's say that we want to design a more complex oracle, right? So we define 3 quantum registers, A, B, C, and we want them to apply this arithmetic expression, right? A plus B plus C and 15, and so on and so forth, equal 4. So take a few seconds and think, how would you implement this circuit? Okay, time is up. So this is how this circuit would look like. This circuit was automatically generated by the Classic platform, and it's quite complex, right? Each of these boxes are functions, and inside each function you have more functions, and eventually when you open all these functions, so you get quite a complex circuit, not a one that would be so easy to build manually. And surely that's a simple circuit. That's only on 22 qubits. So what about circuits for 100 qubits, 200 qubits, 1000 qubits? So obviously scaling is a challenge. And now I want to dive a little bit into these circuit design challenges. So the first challenge is that the software developer needs to take care of block level decisions and system-wide constraints at the same time, right? So what are blocks? What are building blocks? So it could be anything. It could be a state preparation, or entangler, or mixer, or some arithmetic expression, everything like that. And each of these blocks has first many possible implementations, and you can choose the number of auxiliary qubits and the appropriate level of accuracy. But then, in the entire circuit, you don't have one block, you have many blocks, and you also have system-wide constraints, like what's the overall number of qubits, and what's the circuit depth, and hardware constraints like preferred gate sets or noise model or connectivity. And the problem is that these issues are deeply interconnected, so it's really, really hard to do this trade-off manually. The second challenge is that we design these circuits, we need to navigate a huge design space. And what do I mean by huge design space? It means that the same functionality could be achieved with very, very different circuits. So what I want you to do is to focus for a second on the 7th qubits, right? No, I'm just kidding, don't do that. But basically what you see here, so these are entirely different circuits, right? With more qubits, with less qubits, more deep, less deep. But basically they all have the very same functionality. So first, it's very challenging to build even one of them. But second, if you succeed to build this circuit, probably you'll use too many qubits. You will need 200 qubits, but maybe you can reach the same functionality with 127 qubits, and that's popular right now, right? So, okay, so we have a huge design space to navigate, and then, you know, you can ask, okay, what about compilation? So the point is, obviously compilers are very important, but the flexibility at the compiler level is very small in regards to the functionality level, because the compiler, you know, it gets as input a quantum circuit, it's not aware of the functionality you wanted to achieve, and it's bounded to keep the gate level logic, right? So obviously the last mile is automated, but what about the rest of the market? So now I want to give a few simple examples to this large design space, and what does it mean to reach the very same functionality between different design choices. So the first is quite simple, right? So we have a function, you know, this blue box is a function with 2 inputs, 2 outputs. It could do anything you imagine. And 1 auxiliary qubit. So if you want to implement 3 of these functions, you can use it in the naive way, right, with 9 qubits. But then if you embed uncomputation for the auxiliary qubit, so you can save 1 or 2 qubits, right? So that's very simple, but now imagine hundreds or thousands of these functions, so you can reduce by orders of magnitude the number of qubits only by reusing these auxiliary qubits. So that's one example. Another example is factorization, right? Let's say that you need to order local Hamiltonian terms, so you can do that in the naive way, or you can, you know, use the fact that they are commutative and, you know, order them in a more compact way. Uncomputation. So basically you do some operation, and then you can, after you finish the operation, you can add uncompute square and save a lot of qubits. And, you know, when you get to more a complex circuit, so the variability between different implementations is huge. Right, so let's summarize the challenges and then dive into the solution. So basically, building quantum circuits at scale is hard. Navigating this huge design space is very challenging. Doing this trade-off between functionality and constraints and hardware constraints, very challenging. And of course, as we all know, embedding domain experts, which are non-quantum information PhDs in this process, is also very challenging. So basically, that's the problems that we are solving in class. So if I need to summarize in 1 sentence what we do, so Classic synthesizes gate-level circuits from high-level functional models, enabling the design of complex, sophisticated quantum circuits. Okay, so what does it mean? So basically, we solve this complex design challenge. And when solving it, we took our inspiration from another very complex design challenge that was already solved, right? And this is the classical circuit design challenge. So basically what you see here, this is an electronic circuit, not a very complex one, but yet you wouldn't want to design it at the gate level. And you don't need to, right, luckily, because in the classical world we have high-level modeling languages like VHDL, like Verilog, and synthesis tools like Cadence and Synopsys, which basically allow the designer to focus on functionality, to define a high-level functional model of the circuit and forget about implementation, because implementation is automated by synthesis engines. And this is essentially what we bring to the quantum software world. The ability for the software developer to define a high-level functional model of the circuit and forgetting about implementation. And basically what you see here, so this is the exact Grover oracle that you saw before. So all the developer needs to do is define, you know, what he or she wants to achieve. So in this case, this is a specific oracle, and, you know, we limit the number of qubits to 12, and so on and so forth. And we define that we want the output format to be Q-sharp, and then this circuit is automatically synthesized in a fraction of a second. And, you know, this one is simple. It could work on 3,000 qubits as well. So this is the high-level idea, and now let's discuss the flow. So how does the flow look like? So basically, you start with a high-level functional model. You forget about hardware, you forget about constraints, you just define what you want to achieve. It could be some complex financial model, or to design some specific VQE ansatz or anything like that, right? You know better than me. And then you add the constraints, and the constraints could be anything, right? It could be the overall number of qubits, it could be circuit depth, maximal number of CNOT gates, it could be some error correction schemes that you want to embed in the circuit, or anything like that. And then the synthesis engine, takes the high-level model and synthesizes gate-level circuit that meets those demands and constraints. If that's doable, sometimes it's not doable. And then you get a quantum circuit, at the output language of your choice. We are already integrated on top of Qiskit, Q#, Cirq, Rocket, Qasem, and soon QIR as well. So then you just, press the button and run it on the backend of your choice. We are, as I said, integrated on top of leading quantum cloud providers, and we have customers that use basically each of them currently. And the beautiful thing is that when you define a high-level functional model, so then you can load different hardware constraints, and you don't need to tailor-made a circuit each time, which could take a long time. So why is it good for? Basically, it's good for a few main reasons. First, it enables you to build sophisticated quantum circuit in a scalable way, right? You don't really care if you do that for 20 qubits or 200 qubits, because the hard work is being done by the synthesis engine. You need to know what you want to develop, which is hard. It's not easy, but enough trouble without being needed to build a gate-level circuit. Then it also reduces by orders of magnitude the required resources, because, as I said before, sometimes we design some fantastic quantum circuit and you need to use 70 qubits. You don't have reasonable 70 qubits today. And then if you find another functionality, the same functionality with 35 qubits, which we see all the time, so you can run it all of a sudden. So that's very important. It also dramatically reduces the development time, and it enables domain experts, which are not quantum experts, to participate. Obviously, we need quantum experts to build the complex functions, but building models on top of these functions, that's something that domain experts definitely can and should do. Right, so I want to dive into one specific industrial use case that one of our customers was designed. So this is a three-stat optimization solver for the formal verification use case, but it could be applied to many combinatorial optimization problems. So I'm not sure that you see this, but I'll try to explain. Basically, you divide the development into three. First, you define the high-level functional model. In this case, you only define what are the stat equation that should be met. In this case, it's very simple, only three of them, right? Then you define the constraints. In this case, the constraints are very simple. I want to limit the overall number of qubits to 13, and the maximal circuit depth to 5,000, and then I choose the backend of my choice, right? In this case, it's the Qiskit simulator, but as I said, it could be, basically any gate-based quantum computer. Right, so now I generate a quantum circuit, and on the fly, the synthesis engine checks many options, right? Numerous number of options for many different implementations, and eventually it chooses the one that both meets your functionality demands and also the constraints. So this is the optimal one that was chosen. And now let's see some real results. So all of the circuits that I'm going to show are real circuits that were generated out of this high-level functional model, and each is optimized for different optimization criteria. So the first one is optimized for circuit depth. So you can see that, you can't see yet, but you'll see later on that it's quite shallow, but it uses all the 13 qubits I allowed it to do. On the other hand, this one is optimized for qubit count. So it uses only 8 qubits, but it's wider, right? And the third one is optimized for overall parameters. So we get the best accuracy of the algorithm in regards to many hardware constraints. And you see that this is using 12 qubits, and the circuit depth is somewhere in between. Right, so before we finish, I want to describe how customers use Classic today. So basically, on the platform, you have application suites, most of the common industrial use cases in finance, in chemistry, in QML, optimization, and so on. So this was implemented by us, and basically these are high-level functional models of these use cases that allow you to design your own quantum circuits with your own data and needs, obviously. But on top of that, and that's super important, you can very easily create your own custom functions. You don't need to rely on pre-built building blocks. You control your own future, and we see users create very sophisticated functions that after that could be used by the synthesis engine, and obviously it gets better as long as you add functions to it. And then you run it on the back end of your choice. So here are like 3 examples. So this one, actually, we announced last week to be working with entity data. So this is the algorithm developed by them. This is the amplitude estimation for options pricing, value at risk. So you see that the synthesized circuit is functional based, right? So the first part is asset loading. After that, the arithmetic expression. I don't want to dive into it right now, but we can do it after that. Another one is the QAOA based portfolio optimization. Same idea. And the third one is these custom functions. So F1, the pink one was created by me. I defined the functionality, the inputs, the outputs, and now the synthesis engine is embedding this function in a more complex circuit. Right, so I want to finish where I started. This is the time to start preparing to building complex circuits. It's really fun to optimize 7 and 12 qubits, but soon it won't be enough. And basically that's what we do, and you are very welcome to visit us in our booth, preferably with a beer, and love to take any questions. I don't have sunglasses, so if someone has a question, go ahead. I don't see you at all.
Thank you for a very nice talk. I have to say that I like the name of your company very much. It's a little bit provocative to say in a balance connection between classical and quantum. So the thing is, to what level of extent you exploit analogies between classical statistical physics and quantum physics in your methodology of design?
So this is a good question. So first, the analogy breaks at some point, because here the gates are the software, right? It has no implications of the hardware. Having said that, the classical tools of EDA are very, very helpful, and constraint satisfaction and these CSP solvers are very, very helpful in the synthesis of quantum circuits out of high-level functional models. Obviously, it's also very different because quantum logic is different, but this concept of functional-based development is similar in a way. I hope it answers.
Thank you for the presentation. I want to ask, so what are the biggest difference between the synthesis of like a hardware, like HTML, for example, and this classic program, classic synthesis, synthesis and the place routing? What are the differences, biggest differences?
The biggest differences. So basically, what is here? So this is the QDL, the quantum description language, which is our high-level modeling language, which then is injected to the synthesis engine, and you get a quantum circuit. But we also succeeded to design quantum circuits using VHDL, and we do consider using some of the classical EDA tools in order to synthesize these gate level circuits. So, you know, in order to dive more, we need to take some time after that. But basically, the synthesis methods are quite similar. Here, the analogy is not bad at all. And, you know, in our team, we have a few CAD experts, computer-aided design experts, which did this very specific thing in the classical start. Obviously, most of the team is quantum software engineers, but this combination is what enables us to create these synthesis engines. Yes?
Can you say what the performance of your synthesis engine is? For example, if I had a 1,000-qubit circuit, how long would it take for it to find the optimal synthesis?
Yeah, that's a great question. So obviously, you know, the synthesis is also an NP-hard problem in some cases, right? So the beautiful thing is that you don't need to be optimal. You need to be, you know, better in orders of magnitude than what could be achieved otherwise. So usually the synthesis, even for hundreds and thousands of qubits, it will take a few seconds. But, you know, if you do want to let it run for the entire night, you'll get a better result. So it's kind of up to you. But of course, we don't need to solve these NP-hard problems. We have heuristics, and this is kind of similar to chip design, right? The place and route problem in chip design, you know, we are not even close to building that, and yet, you know, our computer is working pretty well. So I hope it answers, but this is yeah.
Thank you very much for very interesting talk. I'm wondering, you're showing how to optimize circuits for quantum computers, and this will depend on the parameters, how many qubits you want to do and so on. But I'm wondering, do you foresee a moment where you will need a quantum computer to optimize it?
That's I would love that. I would love to embed, you know, combinatorial optimization in our synthesis engine, but it's well, we are not there yet. Great. So you can also catch me after that.
Okay.
Thank you.
Thank you very much, Neil. Okay, I have